Ladies and gentlemen, we're about to start. As you know, that's most of the events will be broadcasted online. So if you wish to share the link with your friends and family, you can find it on our Facebook and contact groups, right? It's a great honor for me to start today's meeting. I know that graduates are anxious to present their research, but to start with, I'll introduce the station committee. And please meet Kollege Alexander Antonovich, Doctor of Science, Assistant Professor, Head of Nuclear and Heat Power Engineering Department. I'm Conor Hensley, Doctor of Science, Assistant Professor, Nuclear and Heat Power Engineering Department. Stefano Nicotinho-Giorgi, Doctor of Science, Assistant Professor to Biology Machines and Aviation Engines Department. Lady Constantin Varisic, Doctor of Science, Assistant Professor to Biology Machines and Aviation Engines Department. And Lovin Kisimampiena, Assistant Nuclear and Heat Power Engineering Department, Vice Director for International Students. And the first speaker is Freddy. Aslan Asalpuri, Supply Chain Management of Biofuel Production from Waste in St. Petersburg City, Russia, Waste Processing Locals.
Waste generation is an undeniable fact of human's life and used to be considered as a useless material until the humankind started facing with shortage of energy sources and high demand of energy and the utmost of importance global warming. Then they started investigating on waste in urban areas, and they found it as a sustained source of energy. Dear professors, ladies and gentlemen, for St. Petersburg, during the next slides, there will be two models. First of all, some of the problems and challenges of the current waste management in St. Petersburg will be extracted and discussed, and even compared with two neighboring countries, and then two models in general form of chain management will be introduced, and then two of the common treatment technologies will be evaluated here, and financially and technically, and the potential, the feasibility, and applicability of those treatment technologies will be approved here. First of all, St. Petersburg City is located in a very critical location. Why? Because it has access to the Gulf of Finland, and it can easily spread the pollution to the sea, to the neighboring countries, Finland and Estonia. That's why it is very important to manage the waste and stop leaking to the sea. Comparing the situation in Estonia and Finland, Russia unfortunately shows a high rate of waste generation within 10 years by 2015. And as you see, for example, Finland has kept its rate constant within the same decade. And even Estonia showed a bit decrease during this period. And for the landfilling trend, again, we can see that, for example, both Finland and Estonia showed a big decrease in landfilling trend, which shows they are investing on waste utilization. And unfortunately, again, Russia has a high increase by almost 100% for the same period. And here you can see the treatment trend for all those three countries on Russia sticks to the bottom of the diagram, while both of the countries are almost experiencing the same trend within these 10 years. And there are some other reasons. For example, we can say population, that they have kept the rate constant within these 10 years. As an introduction of the land filling situation in St. Petersburg, we can say that the land filling area occupied in the city is almost 3.5 million cubic meters, and this statistic, this area, is excluded from illegal landfills, because in St. Petersburg we have both legal and illegal landfills, but there is no available statistics about the level of pollution, the amount of waste in those illegal landfills. And it is expected to have 4 million, well above 4 million cubic meters by 2025, and the amount of waste generation in the city will be more than 2 million tons per year. The current situation, the current waste management in St. Petersburg has some deficiencies, especially due to the regulations. For example, if you want to recycle the waste in the city and you want to separate your waste at home and deliver it to some collecting spots, stations in the city, you will receive 10 rubles for a kilogram of paper, and such value will be even less, much lower, for delivering a glass bottle. And if no separation is performed at homes, the citizens will be charged for something around less than 4 rubles per square meter, and it is not going to entice people to do the separation at homes. By the way, a significant deficiency of the system is landfilling almost 80% of waste in the city. It means that maximum 20% of the municipal waste is recycled by two facilities and other facilities that we show you here. There are some companies, some facilities to collect, transport, and dispose and recycle the waste in St. Petersburg, but not for all types of waste. For example, for tire, for mercury containing waste, and not for example, organic waste. Therefore, there are some capacities, but they are not being utilized in the proper way. Current problems in the city can be mentioned as long distance between homes and landfills. For example, there is more than the distance between the city center and the landfill in Gatineau district is more than 45 kilometers. And also, as another problem of the system, managing system in the city, we can mention that, for example, there was an experiment in 2002, and two separate bins were mounted at the streets and curbs, and but people weren't aware how to use such bins, and the experiment terminated in 2009 without reaching the desired results. Also, as I already explained, there are some illegal landfills, and there is no inspection over such landfills. There is no statistics. no protecting structures. Also, lack of state incentives leads people not to do the separation at homes. Insufficient capacity of WTE, waste to energy technologies in the cities, also considered as another problem. No treatment facility except recycling. We have both biochemical and thermochemical processes to treat waste in the city, but we are just using recycling and biocomposting. And the parameter I used to propose a comprehensive cycle for the city is lack of available critical information, because it was difficult to access the critical information about the amount of waste, about the pollution, about the landfilling trends, and that's why it is considered as one of the most important problems of the city. Here, a supply chain is proposed to start using waste in a sustained way. Generally, supply chain starts from producers to the consumers. But here, the model is proposed to consider people as the suppliers of the chain. Then it means that they produce waste, and the waste is transported to the facilities, and then the desired products will be produced and generated in those facilities, and they are vended in the market. And again, people, the citizens, will be used such products. So that's why such strategy is called as reverse strategy. It starts from people by producing waste and utilizing in those facilities. And here it is a comprehensive chain to make the process sustained. And as I already explained, here we invest our time and money and energy on raising the public awareness. And then the waste will be collected, transported, and segregated in some separation facilities. And the statistics about the waste will be classified and shared publicly for scholars, researchers, and university students for further processing, further evaluation. And then the waste, after being segregated, will be sent to the waste processing facilities. And the valueless materials will be disposed to landfills. Therefore, general framework of the models will be based on such supply chain management, and the models will be based on household separation as the first scenario, and the second one will be centralized separation. For the first scenario, the waste separation will be performed at houses. It means that there will be 4 different bins for paper, plastic, glass, and food leftovers. And even it is considered to utilize waste bags with paper, made up of paper, in order to avoid using non-recyclable materials. Therefore, for the householders who do not perform home separation, they will be charged extra tariffs for waste collection and transportation. And we see the scheme of the first scenario as house separation, then collecting and transporting to the facilities, and then it will be treated or disposed to landfills. For the features of the first scenario, we can say about less amount of waste, landfills, sent to landfills, reduction in green raw material consumption, useful products such as fertilizers and biofuels, thermally valuable fuels, the share of biofuel in heat and electricity generation will increase, and due to proposing near location of waste treatment facilities to the center, there will be less cost of transportation, less distance, and less pollution leakage during the transporting to landfills. And for the challenges, we can talk about public awareness, but it will be compensated, it will be improved by providing some TV programs, educational symposiums at universities, promotional activities, and encouraging plans. And they will, as the result, there will be new behavioral paradigms in the society. And for the second scenario, the separation will be done in segregation facilities, but people, householders, are charged for taxes based on transportation costs, collecting and separating. So here, the culturalization will be shifted toward efficient consumption and purchases. And for the features, the separation will be done more efficiently. Again, shorten transportation distances, less fuel, fossil fuel consumption, and air pollution. For the challenges, more land will be occupied in the city for establishing separating facilities, and higher investment costs. But such costs will be compensated by applying taxes. And the separation efficiency will be less economically, less cost effective compared with the first scenario. Therefore, as the solutions for both of the models, at the end of the models, we are going to first produce biofuels and heat and electricity generation. We have these two options, and in the next following slides, I will explain the economical aspect and the capacity of such productions. First of all, for biofuel production, it's better to mention that CO2 and H2 are the substances of biofuel production, and we can extract methane gas from landfills by pulling some piles and extracting the methane and use it to produce biofuels. Also, as an example, 10% of annual gasoline demand in America is supplied by 47 billion liters of ethanol. And as an example, successful examples in other countries, for example, in Finland, 160 megawatt waste gasifier is installed to produce biofuels, and in Canada, commercial municipal waste ethanol facility with annual production of 38 million liters. Estimation for just using 30% of the waste in the city, we can produce 477 million liters of ethanol. And if for 100% and for the 30% of the annual waste, we can produce biodiesel production for 523,000 liters, which is very significant. And for the incineration technology, the production of waste by using 70% of the waste in the city, we can have 3,000 for almost 3,500 tons per day to produce 2,700 megawatt electricity per day and 5,000 well above 5,000 megawatt thermal energy per day again. And therefore, by such amount of energy generated during 1 year, we can supply 158,000 houses with heat and 3,300,000 houses by electricity. For the economic aspect, we have different costs, including investment costs, operational, and net cost, which will be over almost 12 million, and the payback time will be almost 10.7 years. And there will be some further working on economic analysis and locating the best position of treatment facilities through some algorithms like genetic algorithm. At the end, I would like to thank my supervisor, assistant professor, Mr. Ankoma, Dr. Vitali Sergiev, my friend, Mr. Oliver Bianco, for giving me the chance to work in scientific field, and my friend Sultan Makray. Thank you very much.
Thank you. Let me tell you what's academic performance of assignments of Puri. That's 11 excellent grades, 3 good grades, and a review, let me quote, says this work covers various aspects of the topic, including technical, social, cultural, and financial aspects, and thus deserves to be considered as an excellent grade. Do you have any questions?
Thank you very much. It was really very interesting and quite outstanding. From our point of view, the problem here you investigate is very hot issues nowadays, and all of us wanted to push these innovations in St. Petersburg and in Russia in order to make our life much better. But still, from my point of view, you make it in a very, very optimistic way, but definitely there are a lot of problems in order to implement some kind of technologies here in St. Petersburg. And as you did very good work, can you tell us what should be done from maybe the government, city of St. Petersburg, Russia, at first in order to solve the problems?
First of all, it's better to provide a good collaboration between private sector and state governmental sector. By providing some state incentives, government can entice private sector to invest their money on establishing such facilities. Also, there is another task for the government to, as I already explained, to raise the public awareness. People need to know about the global change, about the climate change, about the environmental protection. That's why, by using some TV programs, by using some instructive materials and events, especially at university, as the most trustable places in each urban area, government can involve private sector and ordinary people, local people, at the same time together.
Thank you very much. And also have a question. You told about two different scenarios which you investigated. And the question is like, did you do it just simply investigate it and make some calculations, or did you use some, I don't know, database or some software in order to model it?
In order to model it, there was no need to use any tools because it was obvious that, but by using different databases, first of all, from European statistics, successful projects, from Russian databases, administrative website here in St. Petersburg, in Moscow. There were many databases and resources used. But for modeling, it was easy to it was just necessary to guess the amount of waste we needed here, the amount of suitable waste for each technology. Yes, of course. For example, in my thesis, there's a table available for different types of waste, the percentage of waste in 1 ton here in St. Petersburg, and I had to calculate it. That, for example, for using incineration technology, how many tons of waste I have available and I can use per year. Or for example, for composting or anaerobic digestion, how many tons of waste are available to utilize in such process. That's why it was important to calculate it, separate different, even extract and clean the information from the databases, and then start calculating based on each technology and based on the specifications of the waste system here in St. Petersburg.
But it means that all these parameters, they were average, let's say so, because they were from the different databases and you didn't like investigate the real amount of everything in waste, right?
I cannot call it average values because when I wanted to, for example, know about the waste characterization in St. Petersburg, I could only trust the administration of St. Petersburg, okay? Because that was the right and the most suitable database for such information. That's why I relied on such databases, and I could extract the values. Also, in some cases, I had to calculate the maximum or the minimum values just to get sure about the margins of my calculations.
Are there any other questions?
So thank you for your report. It was very interesting. Could you say specify one moment? So you said that about supplemental heat and electricity of some amount of houses.
Yes.
So I don't remember that very well. What do you mean by houses? We have a large buildings in Petersburg.
Yes. It was considered flats. Yes, flats. Yes, flats. Flat. It was considered for the average area of one flat for the young generation, 40 cubic meters.
Okay.
Okay.
I see.
Yeah. Square meters. I'm sorry.
Square
I'm sorry. 40 square meters, and then when I calculated the whole amount of electricity for 1 year, I could divide it for 300, this is information from the administration of St. Petersburg, 300 kilowatt electricity per year for one flat. And then I could obtain such number of flats in the city.
Okay, thank you.
Are there any other questions? Thank you very much. Before I invite the next speaker, I would kindly ask you to stick to the time limits, which would be like 10-15 minutes for your presentation. Our next speaker is now Sun. The comparison of different post-tryout calculation techniques for power equipment. Supervisor, Assistant Professor Natalia Agapona.
Copied which one?
So the last one. This one.
Okay. Just next, previous, by holding. Yeah, that's all.
Good afternoon, Professor. My subject is about the comparison of different post-trial of dispersal flow bowling calculation techniques for power equipment. Dispersal flow bowling is a consideration that occurs at high void fraction in a liquid channel. And the dispersal flow consists of small liquids and which intrude in flowing vapor, and the heat transfer in post-drought is from the wall to vapor and from the vapor to droplets. The post-critical heat transfer can take place in emergency models with a loss of coolant exit in the pressurized water reactor or boiling reactors, in the ones through steam generators of nuclear power plants with faster neutron reactors under the normal operating conditions, in powerful ones through boilers. There are two kinds of crises in the film body. The first, here is the point of warehouse takes place at high heat flux and low mold fraction, and there is the point of dry out. After dry out is the dispersed flow through boiling, and dry out takes place at the high heat flux. High heat flux, but is lower than the point of dry out, and low and higher void fractions. The aim of my work is to compare. I use the two rather simple engineering techniques for the calculation of heat transfer coefficient in dispersed flow. I just choose simple and technical models. The one is the equilibrium method by Milabowski, and another is non-equilibrium techniques based on the Killing model. And I also calculations with the code for best estimation of thermal hydraulics of circuits of nuclear equipment was also used. And the technical experimental data just as basic data to compare the calculations with the two methods. Now I introduce the Milabowski method. The method is an equilibrium one. The vapor and the droplets are in the saturation state. This is the original formulas to calculate the Nusselt number and the Reynolds number. This is the application range for these models. But in my work, I use these formulas to calculate the Nusselt number. And here is the table for these formulas where can be used. Now I will explain the process of Milabowski method. You can see in this formulas here is the plot number need to be calculated and the wall temperature. But in the first, we don't know the wall temperature, so we just assume the wall temperature just only from 1 to 3 kelvins higher than the saturation temperature. And we need to calculate the physical properties and the given wall temperature and step by step to receive the calculate wall temperature. And then we need to compare the given wall temperature and calculate the wall temperature. If the difference between them is very small and the value are closer, we can obtain the wall temperature. If not, we need to do the cycle again. Another is the non-equilibrium model. Here is the original Killing model. This is the formula used to calculate the non-equilibrium coefficients. This is for original one, but in my work I changed the formulas to calculate the parameters. You can hear these values as average in the coefficients depending on the heat flux and flow rate and the numbers of droplets in the flow. This is all the original, and in my work I will use these formulas to calculate the actual vapor content and the vapor temperature. This used to calculate the wall temperature. Here is the process of calculations by modified Killing model. In this model, we need two cycles. One is to calculate the vapor temperature, and another is to calculate the wall temperature. You can see here the physical properties as the average temperature between the vapor and the saturation temperatures. But we need to calculate the vapor temperature. So we also need to give a vapor temperature in the beginning and to calculate the non-equilibrium coefficient and then calculate the vapor temperature and compare the to obtain the vapor temperature and the given temperatures. They have the similar principle. So if we receive the vapor temperature and then we calculate the actual quantities and use these steps to calculate the wall temperature. We also need to compare the given and obtain the wall temperature. If the values nearly different, just only one, less than 1 Kelvin, we can get the obtained wall temperature and the final temperature. So is the process. We use the computer called Parsa to compare the with the experiment data and the two models. The program was similar to Parsa and made the best estimate code. You can see here in the Parsa.exe is the executive part of the program. In this part, we use the car.doc file for solving problems description. Here, another part of the program is 2.exe is the processing part of the program. In this program, in another file is also used for post-processing of calculation results. Here, this part is the for physical properties calculations. In my work, I calculate the full bandit run number code. Here is the number is 5,340. You can hear is the original parameters. Here you can see the red line is the modified kindergarten model, and the green one is the Miyakoski date, and the black line is Karsa date, and the point is the experimental date. You can see the dry-out point of Karsa and the experiment is have a big difference. So, and you can compare the three wall temperature. The modified kindergarten model is much more suitable with the experimental date, and the Miyakoski is higher than the experimental date. Here is also the same. The dry-out point is also have a big difference between the experimental date and the Karsa. And here the Miyakoski method calculates the wall temperature is lower than the experimental date, and the modified kindergarten model is closer to experimental date. Here is also have the same problems. Dry-out point is different, and modified kindergarten model can be better describe the wall temperature for experimental data. But this run number 5,294, you can see here the dry-out point of Karsa and the experimental data nearly the same, and the modified kindergarten model calculates the wall temperature is much better than the Miyakoski data. Here is the table for X average. X average I used in the equation of 9 kilogram coefficient. You can see that the value of X average is depending on the flux and the flow rate, and X average is also necessary for us to calculate the vapor temperature. But in my calculation, I just calculate the full run mode. But it's too small. I think we can practice large amounts of experiments to compare the X average. Of the conclusion, the review of the literature on the first flow is transferable is done. There are two engineering models which chosen for comparison. The Miyakoski method and the modified kindergarten model. The Bennett cube experiments were used for comparison of these models, just as a basic date. The results of wall temperature calculation based on the King-Galilei model show that obtained values differ from the experiment date no more than 70 kelvins. The Milankovsky method is no more than 80 kelvins. In the modified King-Galilei model, the original method was used to calculate the non-equilibrium coefficient W, and the formula for W is based on the formula by Barzoni and Martin. In which we introduced the coefficient of X average. And the X average is depending on the flux and flow rate. So the next step for the work, I think, is to find a suitable formula for non-equilibrium coefficient X average. The Carsa program can be consistent with the experiment date, so the Carsa program also will be improvement in the future, and it may be done with using of modified environment. Thank you. Any questions?
I think our advice announcing academic performance, that's 10 excellent grade and 4 good grades and 0 satisfactory. Supervisor on this work believes it deserves an excellent grade. Do you have any questions?
So first of all, let me say that I'm really impressed by the work you've done. So it has a great physical and engineering background, and so you have a literature review and you have your own calculation, and you use also a commercial code. I think it can be treated like as a part of even PhD work, but master's is it's really great. So I have a question concerning the comparison of your data with Corsa data and with experimental that were presented on the last few slides, I think, for yes, for example, this one. So we can see on the slides that the agreement usually is better, of your calculation usually is better than Corsa calculations or other calculations. But have you estimated the percentage, so the error that gives your calculation and the other? So can we think not only say about better agreement, that maybe you can give us some figures, percentages of errors, or it's called also uncertainty. So how much it is?
You mean the error analysis?
Yeah.
A different point has a different error analysis because
Not in average.
Average, I think, different run model also has a different. I think maybe in this model it's not very big, just only 3 or 4%.
It's very good for research.
But in Milankovsky is maybe nearly 10% error.
Thank you.
Thank you very much for your work. It was really very interesting, and as you said before, it's nice that you combined here both very good overview and both decisions of the engineering tasks. But my question is regarding slide number 11. There is the model, and my question is like, was it investigated by yourself, this, or it was taken from some authors?
This one, at first I calculated using the original model of Fingerly and another modified Fingerly model, but here is not handy. Correctly describe the superheat of the vapor, so I changed the equations using another by myself to calculate the non-equilibrium coefficient. It can be better describe the superheat of the vapor temperature.
Oh, okay, very nice. And also, like, in introduction, I had one notification to you not to use your fingers while you present something, but then momentarily you began to use the laser, and it was very nice. It was no, that's okay. Thank you.
Any other questions? Thank you very much. As next speaker is Sultan Mahmoud. His masterpiece is Novokuznetsk City Heat Supply Systems Concept Development. Supervisor, Assistant Professor, and Mr. Gimai.
Sultan. Yeah?
Yeah.
Yeah?
I hope so.
Yeah, previous, this first one. Yeah.
Yeah, go ahead.
With your committee, the students again going to present on masterpiece, which is the role of heat supply system in the business city. First of all, I want to mention why I choose this project, because this project currently developing in our university at the Department of Power Engineering, and partly I've been involved in this project. So the content of my master thesis is as follows. So we will go through introduction, general information about the city, current situation in the sector, design of mathematical model in the software, proposal for improving energy system, results and conclusion. So the purpose of my master thesis was the research of the existing heat supply system in the city. Developing of the mathematical model in the Zulu software of the heat supply system, and also to arrange proposals which improve the efficiency and reliability of heating system and suppliers. So this is the general information about the Novokuznetsk city. It's located in Kemerovska Oblast in West Siberia. So it is 4,000 kilometers far from St. Petersburg. The population of the city is roughly 550,000 inhabitants, and heating season starts in October and continues by May. So this is some kind of data for the business city. So the coolest month is January and the hottest month is July. So on this slide, you can see all energy suppliers in the city. And we can divide all the energy suppliers by the group. So the first group is thermal power plants, which are situated in the city. Is Kuznetskaya, or Siberian Central Power Plant, and also municipal and departmental boiler houses. I should mention that all the power plants are cogenerative power plants, so they produce heat and electrical power. So the thermal power plant divided, situated in different districts, as you can see, and the central here and the Kuznetskaya thermal power plants, they mostly supply house buildings, so they supply people. Then the West Siberian power plant mostly supply the industrial consumers. As we can see from this diagram, the energy capacity, so the energy produced by power plants mostly, roughly 80% from the whole energy capacity. So on this slide, we can see the diagram which presents the contractual and actual heat loads in the heat supply systems in percentage. So we can see that on the village study, the boiler house has reloaded by heat and hot water supply, and the central power plant provided by the water supply. The current energy balance divided by sources is as follows. We can see that all the sources has capacity reserve, so we can see that the power plants, the central thermal power plants has the quite huge reserve compared with other sources, other suppliers. So, in distribution of the total reserve available capacity by sources presented also on this diagram. So now I'm going to talk a little bit about the software which was used in this project. The name of this software is Zulu Thermal software. It's drawing form. If we speak easily, so this is a software which provides you to download let's say, to construct the map of the city and put on the map the heat sources and heat grids. Also, you can put the suppliers. So after collecting the initial data from the companies and the administration, you can put your data inside the software and calculate the calculate energy losses, and I will show on numbers on the next slide. You can see the hydrostatic heat and pressure. So this is a proposals which are proposed for improving the energy system. You can see that for each supplier there are different organizations which should be done by the year 2032. So you can see that on the West Siberian Thermal Power Plants there is an organization of technological communication on the pair between first and second floors. This mentoring of turbine grids on the central thermal power plant and commissioning of the hot water boiler. For the initial boiler houses, for this the initial boiler houses, we are going to close them and to switch to transfer the heat load to Kuznetska thermal power plant and to central thermal power plant. These operations will help us to increase efficiency of economical efficiency and to save us the fuel. So the transfers are presented on this graph, the operations which are proposed in the project, and a total of 130 gigawatt-hour boiler capacity is expected to be switched to combined heat and related generation by late 2021. So the projects on the development of the heat supply system in the period in the whole operation of all the period are as follows. So as the main projects, we can see here construction of roughly 20 100 kilometers of heating network to provide prospective increasements of peak load of residential. Reconstruction of heating networks with increase in the diameter. Construction for reconstruction another 70,000 of heating networks to improve the efficiency of the heat supply system, including transfer building houses to peak operation or liquidation of boiler houses. So the results of the modeling in the software are presented here. So on this graph you can see the hydrostatic heat, the hydrostatic head of the supply pipeline and the return pipeline are presented here. So we can see that this graph goes slightly down. It means there are some losses in the pipeline, as the same thing for the return pipelines. After the proposed operations, we will get this graph, and the losses will be decreased by changing the pipelines and increasing the diameters of pipelines. So the proposed measures have a positive effect on the operation of central heat supply systems in our business. So we can see that we can get transfer of the improvement of quality and economy of heat supply is facilitated by transfer of subscribers of a number range of boiler houses. Also, the location of number of heat networks with an increase in diameter. So thank you for your attention.
So the Mahmoud showed excellent academic results with 13 excellent grades, 1 good and 0 satisfactory, and supervisor believes his work requires an excellent grade. Do you have any questions?
So, let me ask a short question. So first of all, thank you for your presentation. It's very interesting. And could you go back to slide number 6? There were some percentages, and it was higher than 100, number 6. So just this comment, maybe I haven't heard the right information. Number 6.
I'm trying.
Okay. Sorry, it's not. Yes. Number 6, yes, number 6. So here, for example, the first 2 bars, they have 100 certain percentages. Could you give some short comments? So that means a bit more than 100. So because it's total amount, so just can you explain me? Because
yeah, this is this boiler house. This is a proposed. So it's slightly remote right now. So they have let's say more consumers for now, but after improvement of energy system, we can get this amount of energy supply.
Energy supply.
Any other questions? Thank you very much. Next is research of application of system in conjunction with water for increasing open units. Supervisors, Assembly Professor, again, Bogan Karamonova, advisor, Екатерина Демушкова.
Не могу закрыть. Презентацию? Да. Да, так ты, короче, быстро не нажимай, либо резко не нажимай, то он не будет переключать. это вперед-назад?
Да, а это кнопку по центру. Ты поставил уже?
Вот она, да. В смысле так?
Да.
Okay, good afternoon, ladies and gentlemen. My name is Reznik Nikolai, and the topic of my master thesis is the research and application of the heat pump system in conjunction with boiler for individual consumption. So the content of my presentation is the introduction, the modern problems of energy sector in the world, and the selection of heat source and the mode of operation for the heat pump, the comparison of different heating systems for the heating, and the conclusions. So here is my aims and objects of the research. So the main purpose of the work was to define the conditions in our region, in the Ingrad region, for efficient operation of the heat pump, for heating, hot water supply and ventilation. So I would like to start my presentation to say why this topic, why I choose this topic, and why I think that this topic is very important nowadays. So nowadays, there are three main problems of the modern and energy sector. So the first problem is the dependence on the fossil fuels. Nowadays, 80% of energy that is generated in the world is generated by the fossil fuels. Next problem is the uneven distribution of these fossil fuels in the world. So this problem causes a lot of social disasters, and for example, the countries that doesn't have fossil fuels, they depend on the supply countries. And of course, the ecological problem, because 50% of the emissions in atmosphere is produced by energy sector. So the one of the main solutions to all these problems is to remove the fossil fuels and to use the renewable energy sources. So on the level of the country or on the level of the world, so worldwide, it is really difficult to do. It is big work to do, and it will cost a lot of time and a lot of investment. But on the level of the individual consumer, it is quite possible. One of the renewable technologies is the heat pump. So the heat pump is the machine that takes the heat from the low potential source and give it to the high potential source, so to the consumer. So this is the main objects in heat pump: the evaporator, the compressor, the condenser, and the expansion valve. So the working fluid in heat pump is the coolant. As the low potential heat source, the heat pump can use air, river water, groundwater, and the heat of the ground. So in the beginning, when you're projecting the heat pump system, the first thing is to choose the low potential source. So on the next slide, this is types of the heat pump systems with different low potential sources. So the first one is the air water type. So the low potential source is air. The advantages of this type is that in comparison with other types, for example, the water type, you can see that the initial investments will be lower, because in the other types there is big initial investments due to the drilling. So you need to drill. to make the heat exchangers. Of course, the air water heat pumps, they are cheaper than well, for example, this one. This one is the water heat pump that takes heat from the groundwater, and here you can see the groundwater heat pump. So in my work, I choose for our region the heat pump type air water. As I said, because it has low initial investments, but the main disadvantage of this air water type is that the air temperature is not stable, and especially in our country. So that's why the next step is to choose the mode of operation of heat pump. So there are two main modes of operation. The first one is monovalent. In this mode of operation, heat pump is the only source of heat in the building. So air water heat pump, it doesn't suit because of the low temperatures in our winter. Uh, so the next mode of operation is violent. There are three violent modes of operation. The alternative, where the heat pump is working until the balance point, so the temperature, until temperature where in this temperature, the heat pump is working efficient or can work. And then the supporting heat generator starts working. The supporting mode of operation, so the heat pump is working until the balance point, but then it doesn't stop. So the supporting heat generator switch on and compensate the heating load. And the last one is combined mode of heat pump operation. So this is most suitable for air water heat pumps, where it is working until the balance point, then it is working parallel with the supporting heat generator, and then it switch off in the very low temperature, and only the supporting heat generator is working. So the next step is to choose the balance point for the mode of operation. To choose this balance point, on this graph there is so the duration of temperatures in hours in different temperature ranges. So as the balance point for our region, I choose the -10 because as you can see that after that the temperatures lower at this point are that consists only 10% of the whole duration of the heating system. So next, I choose the house with area 250 square meters, and I calculated the maximum heat load of this house. So in the bivalent mode of operation, the capacity for heat pump, so the heat pump is selecting for the balance point, and the supporting unit is selecting to the maximum heat load. So as I already said, the type of heat pump is air water, and the type of the heating system is underfloor heating. So here you can see the comparison between costs for heating per heating season for different types of fuel and for different sources of heat. So I also was calculated the consumption of energy during the whole heating season. And as you can see, and also was calculated the coefficient of performance of the heat pump operation. So as you can see, of course, in our conditions in Russia, due to the very low cost of the natural gas, the most efficient heating system will be with natural gas. So, for example, the gas boiler. But in the regions where in ungasified regions, for example, it is more efficient to use the heat pump for example, the air heat pump with electric boiler than to use the electricity to heat. So yes, as I said, that it is economically efficient to use the heating pump system with the electric boiler in an alternative or combined bundle operating mode in ungasified regions. In other conditions, it is more efficient to use gas boiler. So thank you for your attention. You're welcome to ask questions.
Nikolai showed good evidence performance with seven excellent grades and 7 good and 0 satisfactory, and his academic supervisor believe this work deserves an excellent grade. Do you have any questions? Are there any questions?
Let me ask a short question. Thank you for presentation and report. So the main conclusion is that we need diversification, for example, in main work conditions.
Yeah.
So it would be from economical point of view has more advantages, yes, than
yes, in economical point of view, of course, due to the cost of natural gas.
Yes.
Yeah,
But what region can you maybe can you mention some region where your systems would have more advantages in Russia? So I mean maybe you said that some region undecided yes can be used for your mode. What region can you say?
Exactly the region. So it's really hard to say because the region, for example, where there is no central gasification.
So for our country, where can it be?
Where
Introduce such product?
I think there are a lot of. I think in every region there is some places, for example, the villages or the cottage village where there is no central gasification, and the only variant of heating system is, for example, electric, because there is no gas. But to using the heat pump also with electric boiler, it will be more efficient because, for example, the electric boiler will work on like 10% of the whole heating season. But I cannot like say exactly the place, the town or village where there is no central gasification. Yeah.
Yeah, thank you for the presentation. So my question is this. What are you looking at? Are you looking at ramping up renewable energy sources or alternative sources? And what is the investment cost? Initial investment cost for your heat pumps?
Okay, so I didn't understand properly the first
The
part.
first question is,
Yeah.
what is your aim in introducing a heat pump? Because you started by saying that a lot of dependence is on fossil fuels.
Yeah.
So my question is, what is your aim in developing a heat pump? is it just to increase the share of renewable energy sources or cut dependence on fossil fuels, or it is something else? Because in the final analysis, you came out that gas, natural gas, is the cheapest option if it is available.
Yeah.
Now, would you go for a heat pump if you had access to natural gas?
No, as I said, I would not go because economically it will be in our country it will be not efficient. If you already have the heating system with the gas boiler, it will be not good step to change it to the heat pump.
So it's not a question of cutting down on fossil fuel.
Yeah. To cut down the dependence on fossil fuels.
No, you are contradicting yourself. You cannot say if there is gas, I'll go for. You say, yeah. If there is gas, I'll go for gas. I'll not go for a heat pump. So the question is not.
Yeah, but
cutting down on fossil fuels.
I mean, for today, but we don't know what will be tomorrow. For example, tomorrow the gas will cost a lot in Russia.
Very good.
Maybe.
So it comes to my next question. What is the cost, the initial cost of the heat pump?
So the initial cost of the heat pump it will be the cost.
Initial investment. Yeah.
So the cost of the heat pump will be, I think, I know the market it will be something between $8,000 or $10,000 just for heat pump, and I think for the whole to install the whole system, it really depends because it always depends on the house, on the conditions, on the area, and of course the producer of this heat pump. For example, if you will, the producer will be from Russia, it will be cheaper than it will be, for example, Mitsubishi or something else. So it's depends. But of course, the initial investment it will be more than, for example, for just the boiler. But for example, for electric boiler, but you will pay for the heating system in comparison of electric boiler 3 times less for the heat pump. Then, yeah.
Any other questions?
Thank you.
Next speaker is Ling. Comparative analysis of structural schemes of operating parameters and characteristics of stain pumps and displacement pumps. Supervisor, Assistant Professor, Consultant again.
This one, yes. Is it there? Yes, this one.
Hello everyone, my series topic is comparative analysis of constructive schemes operating parameters and characteristics of wind pumps and positive displacement pumps. And now I will introduce what about pumps and materials simply. It's known that pumps are machines that transmit liquid and for transfer mechanical energy to the shaft of the shaft to liquid. And hydrostatic machines are also power machines. They convert one type of energy into another, or transmit energy from working parts inside the machines to fluid flow. The working process of the pumps are continuous, and for positive displacement pumps are cyclic. And my scissors introduction about wind pumps and positive displacement pumps, their design, constructive performance, and the characteristics. And through experimentation, I got groups of these two types of pumps and analyzed the difference from the wind pump and positive displacement pump. This is the energetic scheme of pump, which has the input parameters torque and numbers of revolutions, and with the output parameters displacement and pressure of the main pressure line. And this is the energetic of engine is inverse the input and output compared to the pump. This is the scheme of aerodynamic transmission. It's a cycle. From pump to turbine, the liquid will have energy from pump to turbine and transport the energy to turbine, and then the liquid back to the pump. At first, I learned the design of centrifugal pump because they are widely applied as pump equipment in power station. This picture is centrifugal pump, and this picture is composition degree of single-stage, single-suction centrifugal pump. And this is three-spool pump. The main principal working process is to change the volume of cavities to increase the suction increase the cavity in suction chamber and to decrease the volume of cavity in output chamber. This is the difference from wind pump and positive displacement pumps. I will repeat it in conclusion. This is experimental investigations of pumps. This picture is the scheme of laboratory stand. And this picture is the equipment. There is the tables about the experiment. This table is experimental table, and this table is coherent table. And depending on the coherent table, I made the group of the screw pump experiment. They are dependent on displacement, the working pressure, the power of the shaft, and the total efficiency on performance pressure. And this object of experimental research is centrifugal pump. This is experimental data, and this is the coherent data. Based on the coherent data, I made the proof of this case. They are depending on total head, the shaft power, and the efficiency on displacement. From this picture, you can see the useful point is about 18 liter per minute. per minute when the efficiency is the highest. And conclusions. This is comparing the wind pump and positive displacement pump. From performance parameters, the wind pump and the positive displacement pump have inverse of displacement and pressure. And from performance characteristics, for positive displacement pump, the displacement of hydrostatic actually is not depends on loading P. P is pressure in head pressure line. And for wind pump, displacement of wind pump is directly depends on H. H is in total head, which equals the P. From position, the wind pump has no position, but the positive displacement pump, there are positions with different level. From changing of displacement, the wind pump is complicated with loss of energy. The positive displacement pump is able by not complicated facility with saving of energy. From specificity of design, the wind pump the structures are more simple than positive displacement pump. For production technology, the wind pump is not complicated and is cheaper. The positive displacement pump designs are complicated. They need more accuracy and they are expensive. From efficiency, the efficiency of the wind pump is lower than positive displacement pump. From performance conditions, the wind pump can pump dirty liquid with high rate of temperature. The positive displacement pump is pure, no crushable liquid with not lower temperature. This is communications for application of pumps. According to comparative analysis, it's necessary to recommend different kinds of application for pumps. There are two main purposes of application of pumps: to transmit the volume of liquid from one to another place, to create flow of liquid for performance of actuators in hydraulic power drives. The main conditions are axial wind pumps have good ability to displace great volume of liquid in a short time. Mostly they are applied in the power plant as made circulation pump and another ones which have great displacement. However, the pumps have special qualities. Thermal and radiation resistance. Also, they have closely separated inside cavities from outside environment. They are applied to supply the water in boiler to create the steam for turbine. The centrifugal pumps are applied everywhere, but just with needle bridge. For example, water supply system of civil and plant building. Positive displacement pumps mostly applied where it is necessary to create liquid flow with high pressure. They are in metal processing tools in transport systems as moving transmission and as steering system. There are many schemes of pumps, so it makes difficulty to find the pumps that we need. So great number is needed, but it also permits us to find pump accuracy according to the requirements. Thank you very much.
You showed good academic performance with 3 excellent, 7 good, and 4 satisfactory grades, and his academic result believes this research deserves an excellent grade. Do you have any questions?
Yeah, thank you very much for your presentation. My question is, what was the aim of your work and what tasks you had to solve while coming to this goal?
The aim of the thesis is to analyze the difference from wind pump and positive displacement pump. For example, the characteristics, the working process, and the performance.
The second question, which kind of tools have you used in order to solve these questions?
Tools just calculate by formulas.
By formulas, in Excel file or like in which software? Where
No.
where given this
Without software.
Okay, just by hand.
Yes, that's right.
So thank you very much for your important presentation. My question is about the graphs that were shown during our presentation, some handmade graphs. So that means that you had done some experimental work because you also showed during the presentation it was some experimental rigs, yes, and even a photo of a rig that. So that means that these questions are based on the data that you obtained in some experiment, or
Yes,
it was experiment.
It is based on the correlation data.
On what, sorry?
Calculated data.
Calculated data.
The left is the experiment,
Yes.
the right is
So,
the calculated
But
data.
the left is experiment.
Yes.
So you not only calculated something, but you also took part in experimental work. Or not? This
Yes.
experimental data, you obtained it with your supervisor?
Yes.
Yeah.
Yes.
So there was not only calculations, also experimental work. So it's very important to say this.
Thank you very much.
Now you said it.
To emphasize, yes, because
to emphasize that, yes, because you use experimental data to move to calculations and to make suggestions.
Yeah.
Exactly.
Yes.
That's the point.
Thank you very much.
Thank you. Question. What do you think about the reversibility of hydraulic machines?
I think the pumps may work as engine, and the engine also may work as pump. For a wind pump, it's necessary to change the direction of the liquid. For positive piston pumps, it is necessary just the same and change the pace distributing parts such as valves.
And the second question, why don't apply the hydraulic machine which transmit the energy of position, potential energy of position? You understand my question?
Yes, I understand the question. The energy of position equal to MTH. If to create the energy of position, we need to create M and H. When we create more H, when we create more M of the liquid, it will make a wind machine. And if we create more H, it will make emissions of machines, and this kind of machines are not useful, and they are limited with very low energy.
Yes, thank you.
Thank you very much.
Thank you very much.
Our next speaker is Nikki Bimai. Master thesis is use of heat pumps and technological schemes of combined power plants with CPGT.
Yes.
Supervisors
yeah.
Assistant Professor.
Good afternoon, dear Commission and colleagues. I'm glad to present my master thesis. The topic is the use of heat pumps in technological schemes of combined power plants with combined cycle gas turbine units. So, let's start with the content. I will have the introduction, selection of the heat pump scheme, the economical calculations and economical conclusions, and general conclusions. So let's move to introduction. As once our president said that we have a problem with rational use of natural resources, and unfortunately we still can't solve it. And we allow ourselves unacceptable extravagance. As an example of that, I can say that we lose a lot of low potential heat in cooling towers every day. Why? Actually, we can use it. And as a result, we'll save the fuel and reduce the emissions of low potential heat in cooling towers. As you know, St. Petersburg has an open heat water supply system, and this system requires a lot of supplementary water. And supplementary water goes to the aeration before the system, and it's supposed to be heated. I propose to use a heat pump to heat it before the aeration. As an object, I consider the Pravobережная combined heat and power plant number 5 with a combined cycle gas turbine unit located in St. Petersburg, Russia. Okay, let's move to selection of heat pump. For the calculations, we're considering 2 working regimes of the station, winter regime and summer regime. And for these regimes, I calculated 3 schemes of heat pumps. The first one is one-stage vapor compression heat pump. The second one, vapor compression heat pump with regenerative heat exchanger. And the third one, vapor compression heat pump with regeneration and subcooler. So let's move to the schemes. The first one, as I already said, vapor compression, one-stage vapor compression heat pump. Here you can see exactly the heat pump. Here the circulating water, the cooling tower, low potential heat source, and here the high potential heat source. After the heat pump, it goes to the aeration. So the scene number 2 is pretty similar, but it has a regenerative heat exchanger. And the third scheme has also a regenerative heat exchanger and subcooler. According to the results of calculation, for my condition, the scheme number 3 was the best option because it has the smallest mass per rate of refrigerant and the biggest exergy efficiency. For economical analysis, I considered this scheme, number 3 as I already said, with different rated power of heat pump, 10, 20, and 30 megawatts. So, you may have one question for me, like where exactly I can save the fuel? So the answer is that heating boilers, water heating boilers. For the economical calculation, it was needed to analyze the working regimes of these boilers. Station uses the boilers type of kilogram 100. And here you can see the diagrams of it has access with gas consumption and heat productivity of the boilers. So the bottom curve is below using the heat pump and the upper with heat pump. So and here are 3 diagrams for different rated power heat pumps. Okay, let's move to the next one. Finally, all my economic results I collected in that table. So you can see the heat pumps with different rated power, 10, 20, 30. And let's go to the savings. Okay, it has the minimum and maximum savings because of, as I already mentioned, the gas consumption depends on the working regime of the boiler. So it might have the minimum and maximum. Then losses, it means that expenses for the drive of electric motor for the compressor, then service expenses, profit, it also has minimum and maximum, capital costs for different rated powers, and payback period, also minimum and maximum. And for conclusion, to make a conclusion, I was calculating the average playback period. The results you can see here. So, let's go to conclusion, general conclusion. In open heat water supply systems, it's sufficient to use a heat pump to heat the supplementary water before the aeration. And by all my calculations, in my conditions, the most efficient scheme was heat pump with regeneration and subcooling. And the shortest average payback period was shown by the heat pump with rated power 30 megawatts. So thank you for your attention. Welcome for questions.
In keeping nutshell, excellent academic performance with 9 excellent, 4 good, and 0 satisfactory grade, and his academic supervisor believes that this independent work deserves an excellent grade. Any questions?
Thank you very much for the presentation. The problem of implementation of heat pump technologies on the existing CHP is very interesting and hot topic nowadays. But my question is, like at the beginning, you began to say about the cooling towers that you suggest to use for cooling the air, like the introduction of heat pumps technologies. But do you know if there are any other ways to cool the air in the cooling towers?
To cool the air. Okay, I will show it here. Actually, I cool the water in this circulation circuit with cooling tower, which goes from the condenser of the turbine. And your question is about the cooling air or water?
If for example, like one of the way to make this scheme working is to implement the heat pumps.
Yes.
But are there any other variations? What also you can suggest here, or is only with heat pump and that's it?
No, actually it's not. We can use any refrigerating machine or whatever. Also, in my opinion, we can use, for example, heat exchanger. Just for every station has their own, let's say, like heat needs. So we can use any heat exchanger to own needs for heating or for water supply for the station.
And the second question is like, what's in general, which kind of heat pumps do you know?
Okay, it depends on the way to see. For example, it can be, as my colleague already said before, it can be air, water, water, or groundwater types of the heat pump. And in general, like technically, it can be compression and absorption types. So here is a vapor compression heat pump. It's just simple scheme of one stage heat pump.
Any other questions?
Yeah.
What is the life cycle of DuPont?
Okay, in my work, thank you for the question. In my work, I consider the 15 years, but actually the heat exchangers here can work like 30 or I don't know. And for example, let's say like the smallest lifetime will be in compressor and motor. So, for example, after 15 or 20 years, we can replace it and it will be still working. So,
How much is that?
what?
How much does it cost?
I can show the capital cost of
The replacement part.
the replacement part. I would like to say that we need to ask some companies to have a commercial offer to.
I know, but how much will it cost? How much is it costing now?
Now I have the capital cost of a whole.
Okay, so you did not look at the various parts.
Yes, actually, I was considered that, as I already said, the lifetime 15 years. So I was calculating all the data about this one.
Okay. So theoretically, after 15 years, you have to buy a new pump.
Yeah. But in my opinion, it's not needed. Actually, we can replace.
Yeah, we can. Sorry.
But it will depend on the operation. So.
My question is like also like where to buy the heat pump in 10, 20 or 30 megawatts?
Okay, in general, I would like to say that it's not like just one heat pump. It will be like several heat pumps. And for example, we have quite enough producers in Russia also, and in Europe, for example. In Russia, I know the producer, the FTI, named Minsk. Then in solar investment and a lot of distributors, for example, of Viessmann or something like that.
But their like unit capacity is generally less than 1 megawatt. So you want to buy a lot of and then install together in one capacity.
But actually, one company, Mamo, called Mamo, so it has a unit with 2.5 megawatts, one.
If I may ask, how is it picking up with investors? Because you have equipment ranging between 80 and 240 million, right?
Yes.
With a life of 15 years, but a payback period of 4.5 years.
Yeah.
So it is something which is very good economically, because we take 5 years to pay for the investment and get 10 years milking the project. So how is it accepted? How many people, how is it the market accepting this pump replacement?
The market, you mean the stations? Like,
Yes.
in general, the customer. Okay.
Whom are you targeting? Who is your target market?
The target market is the stations with combined cycle gas turbine units.
Okay. So
and
how are investors responding to these changes?
like in general in Russia, I would say that we have a lot of difficulties with implementing such equipment for the station because of, okay, let's say our stations is really conservative and it's supposed to have like at least experimental laboratory or something, and then maybe it will be interesting in that. So right now, as I know, in Moscow there was one laboratory with heat pump working in the station, but actually now they don't have any investment and it's not working, unfortunately.
Any other questions, comments? Thank you very much.
Thank you very much.
Next speaker is Aftarzet, Design Rules for Steam Condensate Systems, Supervisor Professor СПбПУ and Professor Vitaly.
Okay, hello everybody. My name is Aftarzet and the topic of my master's thesis is design rules for steam condensate systems of steam power plant. So under this heading we are going to talk and we will try to answer the what, where and why questions related to condensate. Like, I mean, we will discuss what is condensate, where it generates a steam power plant and why is it important. Then we will discuss the objectives and scope of this study, and then a typical condensate system of steam power plant
basic presented. There's some major components of the system, and just acknowledging the importance and problems related with the condensate system. Then we will consider some design rules for the optimum design of steam condensate system. Then I done one simulation just to figure out how the condensate flow direction is affected by in upward inclined steam pipes by different vectors, and approach software was used for data analysis. And then in the end, we will talk about the possible future work on the topic of steam condensate system.
Video, yeah. Student, this is a video.
Is it the video?
Yeah.
It's not show the video.
There's no button. So is it possible to play it separately?
No, actually.
No?
Maybe.
Yeah.
Can you continue without the detail?
No, it's not working. Can you go to the playback? Where is that option? There was one option. Is there some option that they are saying to play the video automatically?
Is it not this already? No, it's already.
Can we connect or my laptop?
Take after 20 minutes.
Continue the
Yeah, but then okay, so basically it's a steam boiler. Steam is used by heating feed water, and the feed water we make it separated in the barometer of the steam generator. And I cannot show that figure that I just wanted to explain that what is the difference between the latent heat and the sensible heat. But let's say that sensible heat is the heat that we need to convert saturated water to saturated steam. And likewise, when steam loses this latent heat, it changes back to the condensate. And this condensate is very important because this is treated water, and it has the same temperature and pressure as the saturated steam. So basically, condensate comes in three locations in steam power plant. First is the condenser. We all know that in the condenser we have this cooling system where we cool down the exiting steam from the turbine, and then we have condensate. And also condensate generates in the feed water heating system where we have extracted steam from the turbine that is used to heat up feed water in the feed water heaters. Like in this reforestation regeneration process, we can see that at points 5, 6, and 7, we have extracted steam, and they will transfer the latent heat and convert into condensate. And the condensate is then cascaded backward from heater 1, 2, 3, and finally to the condenser hot bed. And then we have some condensate generated in the steam pipelines that can causes many problems that we will discuss in a while. So, like I said, this condensate is important because when we have this expansion in the turbine, so then we condense this heat from saturated condition to the saturated water condition. And during this condensation, the temperature and pressure remains constant. So that's what I wanted to say that that this condensate contains about 10 to 30% of the total heat contained in the main steam. And that's why if we can recover this condensate economically, then we can reduce the boiler fuel demand from 10 to 20%. But like I said, that there are some problems related with condensate. The main two problems, one is water hammer, the value is not playing, and the second one is the flash steam. So basically, water hammer occurs when we have condensate in the steam pipelines, and if we are not removing it properly, then those slugs or condensate are pushed by the high velocity steam, and this water hammer occurs. And the consequences of water hammer is we have these problems with the pipework equipment, fractures in pipeline fittings, and then we have some loss of live steam. Similarly, flash steam generates due to pressure differences in the pipelines, and the bigger this pressure difference between the piping network, the more we have flash steam generation. And this can result in huge velocities because as the condensate changes into flash steam, the total volume increases by almost 1500 times. So we have a huge increase in volume, and this can result in huge velocities in the pipeline. And also this can result in vapor clouds. Vapor clouds are when we release the flash steam directly to the atmosphere. So they can deteriorate the working environment. So the objective of this study was to design the condensate system in such a way that we can reduce the boiler heat demand, and we can reduce the failure rate of the equipment, especially like pipeline equipment, and then reducing the environmental hazards if we are recovering the flash steam. So, but like we can say that in such a short period of time, we cannot say each and every rule for whole system. So in this study, the most important design parameters and recommendations from the specialists and companies who are dealing with the design and operation of condensate system will be presented. So this is a typical condensate system of a steam power plant. Here we have this is expected steam from the low pressure, intermediate pressure, and high pressure. But here we need to notice one thing, that these dotted lines, solid lines, are the condensate that is produced in the condenser hot well, and it goes. We can differentiate in such a way that this is the feed water that is going to the heaters, and then the expected steam is going to the heaters where it transfers heat and changes into condensate. And these drains, these are the condensate drains, then we passes from a number of equipment like flash vessels, this one, and then we return it back to the condenser hardware. So this is what I wanted to say, because some people say that condensate is everything that is going from the hot well to the feed water heater. But this presentation and this research work was about how can we design this system that is going from the heaters back to the hot well, we can take it to the theory. So some components of condensate system, again, steam traps are really important because these are automatic valves and those are used to remove condensate from the steam pipelines. And then we have some flash vessels. Flash vessels, as you can see that this is a low pressure line and this is a high pressure line. And when this pressure difference occurs, some of the condensate changes into flash steam. So this flash vessel is used to separate this flash steam from the condensate. And then we use some kind of strainers. Those are used to remove dirt and other solid particles from the condensate and steam pipelines. Then we use some valves, pumps that can be covered in a different topic. And steam drain system. Steam drain system is basically before starting steam power plant, we have to warm up the steam pipelines and the valves. So in that condition, we need this steam drain system and that the steam that we are making this steam pipe heating. So then this goes from the pipelines to a drain receiver or collector. Similarly, we have this extraction system which is dealing with the extracted steam taken from the turbine. Then heater drain systems, as I said, these are the lines from the heaters back to the condenser hot well or the deaerator. And then we have some vent systems to remove air and other non-condensable gases. And then this condensate drum system is also part of the condensate system, which is used to maintain a proper level in the condenser hot well. So in situations where we have more condensate in the condenser, then this is dumped into the condensate storage tank. And when we need more condensate, then it is pumped back to the condenser hot well. So now coming to the design rules. So the first and most important step in the design process is the piping network. So basically we can have more options, but I talked with my supervisors and he said that yes, we can have at least 3 options. So in the first option, simply we drain the condensate from the heaters into the condensate tank, and then from there we can transfer it to the boiler directly or to the deaerator or to the condenser hot well. So this piping system requires little attention during operation, but the problem is if you are doing this, the heat is dissipated in the condensate tank and we cannot recover the heat from the condensate here, so the heat is dissipated. In the second option, we cascade this condensate from the heaters, from the higher pressure heaters to the lower pressure heaters, and after that we can move it to the condenser hot well or deaerator. But here the problem can be like if here the pressure is higher and it's low, so we can have huge velocity in these lines that can damage the piping network and let's say equipment and other fittings. And then in the third option, we can put some flash vessels to remove the flash steam from the condensate and then take it to the condensate return line. So basically in these 2 options, we can recover the heat from the condensate, but here we cannot. So it depends on the efficiency and economics of the system, what we need and what kind of piping network is more appropriate. Yeah, the second step is to decide this slope for horizontal steam and condensate pipelines. So we have horizontal pipelines and then we have inclined pipelines. And by inclined pipelines, I mean we can have upward inclined steam pipeline. So for the horizontal pipelines, there are some recommendations for the slope because this slope is important because if the lines are horizontal, the condensate can accumulate in the steam pipelines and they can result in water. So these are some suggested slopes, but generally we can say that 1:240 for the horizontal steam pipeline is a suitable slope. And this is what I mean by condensate system. So this is a steam made, we have condensate in it due to radiation heat losses. The condensate goes to the direct lake, we can say drain pocket. And from the pocket, it goes to through the drain line to thread. Then we have a steam thread. The thread opens only for the condensate, and the condensate then moves to the discharge line from thread to the common return line. So we will discuss this thing in a while briefly. And these drain line to thread, in the literature I studied they should be kept as small as possible. Minimum less than 2 meters. And if these are long, then the steam can fill in this line and we have steam lockage. In the discharge line we will discuss later. Swiftly, we need this key in situations where we have some specific kind of threads. I didn't mention steam threads. So basically we have a mechanical, thermodynamic and thermostatic steam threads. So in some threads we have blast discharge that result in huge velocity and mechanical stresses in the pipeline. So the purpose of this swiftly is to reduce the pressure, the velocity of the steam pipeline and the mechanical stresses. Okay. So sizing discharge line from steam traps. The general rule is these lines should be designed according to the width, speed, recommended velocity, which is 15 to 20 meters per second. And an effort should be made, the lead time should be made as short as possible. And then you can have some problem with the other side line.
Wait, sorry to interrupt you, but can you please summarize your work?
So okay. So this was one analysis done in the Epros software where we have this condensate in the pipeline, and these are the upward inclined steam pipes. So when we increasing the steam flow rate, the condensate will move upward with this steam velocity. So the purpose of this analysis was to find out that what are the factors that can affect this condensate flow. And in my opinion, it was observed that the steam velocity does not change it with the length and the temperature difference between the pipe inlet and outlet. And then this steam velocity, which is needed to push the condensate upward in steam pipelines, is inversely proportional to the pipe flow area and pressure difference. And the effect of variation in pipe elevation is negligible at lower condensate mass flow rate, but it is at high condensate mass flow rate is this steam velocity is needed for upward flow of condensate situations. So in the future we can work on the topic more because the time was short and some experimental work should be done to understand at least what is the behavior of two-phase flow in upwarding plant heat pipes. Thank you for your attention. There was some problem with those videos, so I'm sorry about it.
Henrik showed excellent academic performance with 13 excellent, 1 good, and 0 satisfactory grade, and his academic supervisor believes this thorough and preserves an excellent grade. Do you have any questions?
Yeah, on this slide, first, thank you very much for your work. At the last slide, there is this word. Thank you for your attention. Do you have any comments, questions, suggestions? I have one suggestion, like you, according to the last slides, I understood that you really did a great job and you investigated a lot. You have models and different graphs to show us. But from my point of view, your presentation was very long. You tried to put as much information as you had. And my suggestion for the future is to start from the most important things of your presentation, so then to lose your time and to hurry up. And the second question is, what was innovative in the work? What do you think? Innovative. Innovative, like what was
Innovative
new?
is this whole topic is a new topic. No one is talking about condensate system. We only talk about the steam because steam is very important in steam power plant. So everyone is talking about this system. The steam that is going to heat up the feed water heaters. But no one is talking about the condensate. What we need to do with the condensate? What are the problems with the condensate? How can we design this network? So this is totally new topic, and we cannot find this topic in the books. We can find, but maybe some sections, like I said, that we can find some chemistry, how condensate changes in chemistry. But there is no direct link or source that you can say that go to this book.
What was your literature source? So I mean, like in which country or maybe
So
which
mostly-
professor is nowadays the most outstanding in this field?
So mostly those were the references were from the companies and industries who are dealing with who are specialists in the condensate system. And you can see in my notebook, so those are the European sources. Yeah.
Thank you very much.
Thank you.
With master thesis, organic franklin
Should I take it?
simulation industrial waste recovery. Supervisor Professor Ramonova, advisor Professor Scala.
Hello everybody, my topic is organic working cycle, basis recovery design and simulation in the ceramic industry. Actually, organic working cycle is a new field in power generation for low and medium grade heat sources. That's we can generate energy from steam working cycle. So we can use organic working cycle because organic waste in this system have better efficiency than steam. And also there are some applications we can use solar thermal, geothermal, oceanic biomass, combined heat and power, waste heat from power plants, and waste heat from industrial process that we concentrated. Energy trends in the world is like now we are here. almost developing countries as non-OECD organization, energy cooperation and development for developing countries and developed countries, OECD, they are the same now. But in 2040, it will be the developed countries almost it's the same. But developing countries is almost twice. And totally demand for energy consumption is increasing. By 2040, it will be like 48% energy consumption will increase. And nuclear, renewable, coal, natural gas, liquid, all of them they are increasing. And we need something to increase the performance of energy generation. And waste heat recovery, we can use temperature from 100 to 400 because before 400, steam brightening cycle doesn't have efficiency and we can generate energy from it. In 100 Celsius degrees, like for geothermal, and after that industrial processes, 200 solar, 300 and some internal engines is till 400, sometimes 450, it depends. So now in European countries, more than 140 terawatt hours, they are generating recoverable energy generating, and it's almost 40% of the heat used in the industry. And it's a big amount of energy. And here we have comparison with between organic reacting cycle and the steam reacting cycle. Especially in this figure, we have organic reacting cycle and steam turbomachinery comparison. In organic reacting cycle, in steam reacting cycle, we have small fast-moving motors that is called erosion in blades and turbine, and also we have we need multi-stage turbines and higher speeds. That it costs a lot. But in organic reacting cycle, we have large flow rate with large motors and smaller rotation plates, and we have less stages for turbine. Also, efficiency of turbines can be like 85 to 90%. It's larger than the steam reacting cycle. Also, organic reacting cycle has higher thermal efficiency in that temperature, under 400. Also, the turbomachinery of organic reacting cycle is less complicated than the steam reacting cycle, and organic reacting cycle totally is less complex than the steam reacting cycle. Here we have ORC market, organic reacting cycle, totally from 1980s. Organic reacting cycle came to the market, energy market. Until now, we have more than 200 projects and total 2,000 megawatt electricity that's installed around the world. And here we have equipment list of organic reacting cycles that heat exchangers that we use for operation, for preheating, also for condensation, and internal recovery in the system. Also, we have the expanders. We have two types of expanders, like turbo machines and volumetric or positive distillation device. That the second one is we can use it till 100 kilowatt. And pump and generator unit. Here we have the sources that we can generate energy in organic reacting cycle, from solar directly to the ORC system, geothermal also directly, fossil fuels in industry, and also in power generation, power plants, after steam turbines or gas turbine, we can use ORC, and biomass gasification, digestion, combustion. Also, we can use ORC as a second technology. And here we have temperature of different heat sources for ORC systems, from cement, steel, glass, chemical processes, food, industry, ceramic, and internal combustion engines. That we are concentrating ceramic industry, that temperature is between 200 to 300. Here we have efficiency of organic alkene cycle as a function of pressure, inlet pressure of turbine that we can see here. Here we can see when pressure in inlet of turbine is increasing, the efficiency also increase. There are two working fluids. We have methanol with low complexity, low complexity, and NDM is high complexity and is more like 40 or 50 atoms in this working. Also, we have organic fluid commonly used in organic systems, organic cycle systems. Upon to GWP, it's global warming potential, and here flammability, that 0 is non-flammable and 4 is extremely flammable, because we have to consider the fluids which we want to use in system, and because more flammability can cause some problems and it's dangerous. But in this study, they choose the R245F8 is our working fluid. That here, this working fluid is actually in this temperature rate is one of the best, actually the best working fluid that's used in some experimental works and some studies, some simulations. Totally around the world, just 2 experimental work on cement, ceramic industry have been done. One of them in 1980s and one of them 2013, both in Spain. And there is no other experiments about this. And we have properties of working fluid, LDN, atom number, critical temperature, critical pressure, minimum temperature, maximum pressure, and GWP, global warming potential. And here we have problem definition. That's relative in advanced factory. Advanced factory in Iran that we considered, and with real data, temperature in exhaust gas from killings from 190 to 210, and the flow rate, gas flow rate is like 15 square meter per second. Is like 54,000 square meter per hour. And here we have simulation with Aspen Plus. Aspen Plus actually is the best and most powerful software for processing simulation and optimization. Here, we choose 3 fluid: water and working fluid, and air as a thermal fluid. And then it's water system design. In this case study, we have evaporator, turbine, condenser, and foam. And here we have result that 291 kilowatts from turbine. We got power generation, and also pump consumes 21 kilowatts. And here we have, actually I simulated this study with different pressures from 5 bar to 36. That the best pressure, it's like here 30 or 31, that we have in 290 or 291. But here we can see in this pressure, we have 220 kilowatt consumption for pump, and in 31 we have 21. And more than this pressure, we have that much work we generated, but we have more consumption for the pump. So it's not throwing power, it's not logical to use more powerful pump or that consume more energy. So the best and optimized pressure is like 13 or 31, as you can see here. And here we have efficiency of the system. It's Q or total heat we got in. This system is like 2,120 kilowatt, and we got 270 kilowatt net power, and efficiency is like 13.72%. And economical aspects of this system, ORC installation cost for each kilowatt is like $2,500. In this case, we have 270 kilowatts, so we have this much cost for installation. And waste recovery, electricity pricing around that, government buy electricity from generator from power plants or waste recovery system. And electricity production is like for 8,000 hours in 1 year, it's like that much. And annual income is like this, because we don't have time to with them. And totally payback time will be almost 4 years for this system. And conclusion for this system, totally efficiency of ORC systems is between 5 to 22%. It depends on temperature, mass flow rate, working fluid, and pressure of turbine. And also we can improve the ORC system with range of thermal, exergy efficiencies, and reduce the cost. Actually, it's a problem with some companies that they are manufacturing ORC systems like Ormat, like Turboden. They are the biggest company. One of Ormat in USA and Turboden is in Italy. They have this much cost, like $2,500 for each kilowatt, but it will decrease in the future. But it needs time. It was more expensive for 3-4 years ago, and now it's like that much. And in this study, we started to design and simulate this waste recovery system for ceramic industry, because in Iran we have more than 100 ceramic factories, and we have a lot of losses in this industry. And also it's a good start to develop this system for different industries like steel, like cement industry, and we can increase the performance of thermal system totally in different industries or power plants, and decrease CO2 emissions. And thanks for your attention.
Thank you. Teaching showed good academic performance with 8 excellent, 6 good, and 0 satisfactory grades, and his academic supervisor believes his independent work deserves a good grade. Do you have any questions?
I have a question. Please show page number 40. What is the unit of measuring of now next down? No, that answer, what do you apply the unit of measuring of pressure?
Of pressure is bar in this.
What?
Bar.
Bar, yes. The maximum in your table is low than the, what is the
pressure?
The table with pressure. Maximum pressure and other pressure. Oh, yes, this. No, before. Critical.
Critical pressure, yeah.
Height, it's bar.
Yeah.
Bar. Maximum, yes.
It's actually it's a table for this temperature. Actually, it's from resource that I used it.
200 megapascals.
Yeah, it's like megapascals.
Yes, I understand. Thank you.
Yeah. It's I got it from the source.
Any other questions?
Thank you very much. At this stage, the Commission will now discuss the results of your presentation, so we kindly ask you to wait outside.
Awesome.